Good evening, everyone. This is week 8 introduction session. Today we will be discussing on the topics of the videos covered in week 8 of our lectures. So, in week 8, that is this week, mostly the course is about some advanced topics. That is pressure velocity coupling, or how to solve pressure equations, and also how to do the simulations for our incompressible flows. So the topics you may find it somewhat difficult, but these are some basic or fundamental information or knowledge about how we can solve pressure equations. Actually, pressure in most of the times in some of the field, pressure is a desired result, but in incompressible flows, the coupling velocity pressure coupling is somewhat difficult. So simulating for pressure, to simulate for pressure, we need special techniques or special methods, and the 4 to 5 different methods for pressure velocity coupling and solving of pressure. That is what been explained in the week 8 of our content. So let's move on to our questions. So first question, in the context of artificial compressibility method, which one of the following is a key parameter? Repeating, in the context of artificial compressibility method, a key parameter is which of the following? Option A, Reynolds number. Option B, Mach number. Option C, artificial viscosity. Option D, Prandtl number. Option D, option D, Prandtl number. So try to answer the question. Simple question only. So we have gone through the lectures. The artificial compressibility is a concept that will be bringing to couple the pressure and velocities, and to bring this to introduce pressure term to the equations. So because in our continuity equation there is no pressure term for our incompressible flow. Incompressible flow, you also know that del dot u is equal to 0. That is what is governed by incompressible flow. And also keep in mind that incompressible flow and incompressible fluid are two different concepts. So what we are uh, discussing here is about incompressible flow, not incompressible fluid. Incompressible flow means by which of its flow the fluid act as an incompressible, the fluid becomes incompressible. That is this condition del dot u becomes 0. That is what uh, uh, because here there is no density term. So in that concept, it's a flow property. Incompressible flow is based on flow property, not the fluid property. Whereas incompressibility of a fluid is mm, uh, the concept from how pressure uh, has influence on the uh, volume of the fluid. So if pressure can vary, if suppose the variation in pressure can vary the uh, volume of the fluid or density of the fluid, then it is called the incompressible fluid. Whereas incompressible flow is a flow property, something defining a flow. So for incompressible flows, one of the earlier method is to introduce an artificial compressibility factor. So from itself, this word itself, you can guess what it is the thing. What is the answer? The answer is artificial compressibility rho star. Rho star is given by P by beta square. So beta is a introduced parameter to solve the equation. And also our continuity equation in artificial compressibility method, our uh, uh, continuity equation becomes dou by dou t of O star plus del dot u is equal to 0. Here this dou by dou t of rho star, this will be running in pseudo time iterations. So the method is in artificial compressibility method. The method is to march this time march this equation, discretize this and time march this equation to a steady state, so that we can eliminate the assumed factors or this newly introduced parameters. So here it's given artificial density rho star is a non-physical parameter, so that we are just imagining it. We are just introducing a new parameter for the sake of coupling the equation, pressure velocity equations. Next question, question number 2. The primary purpose of the artificial compressibility method in CFD is to. What is the primary purpose? If you have to break down the question, what is the primary purpose of the artificial compressibility method that we have discussed now in CFD is to? Which of the following? Option A, directly solve compressible flow problems. Option B, introduce a fictitious time derivative of pressure. Option C, eliminate the need of pressure velocity coupling. Option D, model real world effects of compressibility in fluids. The options are, first one is to directly solve the flow problems. Option B, introduce a fictitious time derivative for pressure. Option C, eliminate the need of pressure velocity coupling. Option D, model real world effects of compressibility in fluids. Let's try to answer the question. Yes, we have just now discussed that we are uh, introducing a fictitious term, that is a fictitious time derivative term with respect to pressure. So in artificial compressibility method, we will be defining rho star and this rho star is used in dou by dou t of rho star in continuity equation. So this term rho star is a fictitious term and we are using this rho star as a time marching for time marching of as a time derivative. So you can say it's a pseudo time derivative. So for actually with this method, why it is known as for incompressible methods, there is no incompressible flows, there is no rho associated with the continuity equation. There we are introducing this rho star, a fictitious time, to include the pressure influence there and to use couple the that is to include pressure in our continuity equation also. So our answer is option B, introduction of a pseudo time derivative. Next question, question 3. Compared to traditional pressure based solvers for incompressible flows, the artificial compressibility method has which of the following? So the question is to compare between pressure based solvers for incompressible flow and artificial compressibility method. Options are our artificial compressibility method always achieves faster convergence. Option B, it may require additional computational resources. Option C, artificial compressibility method is inherently less accurate. Option D, it cannot handle unsteady flow simulations. Try to answer the question. Options are option A, always achieves. That is our artificial compressibility method always achieves faster convergence. Option B, it may require additional computational resources. Option C, it is inherently less accurate. Option D, it can handle unsteady flow simulations. So our answer is option B. It may require additional computational resources because we already discussed that we are introducing a new term rho star that is in form of dou by dou t of rho star. So that is this term need to be discretized in time. This term need to be discretized in time and it should be time marched up to steady state. Then uh, so this thing need to be time marched to steady state so that the influence of this term should be removed from our solutions. So this whole process will be needing some additional computational cost. So compared to other pressure methods, pressure based algorithms or solvers, here we have a transient time, but that is time pseudo time uh, transient time is there, which we should uh, iterate in a pseudo time iteration loop, and we should take that to a steady state condition. That is, this time should reach a steady state so that the effect of this transient time is nullified in the solutions. So that's the difference between artificial compressibility method and other pressure based solvers. Moving on to next question. Which of the following statements about the artificial compressibility method is false? So the question is about which is a wrong statement from the below is false about or wrong about artificial compressibility method. Option A, it requires a careful selection of artificial density parameter. Option B, it can be used with various discretization schemes like finite volume methods. Option C, it eliminates the need for solving separate pressure equation. Option D, it is a popular approach for simulating turbulent flows with incompressible conditions. The question is to find a wrong statement about artificial compressibility method. Try to answer the question. So if you can go through the options. The first option is to request a careful selection of artificial density parameters. Actually, we have already defined what is artificial density parameter rho star. So that is not something false. Next thing, next option, uh, it can be used with various discretization schemes like finite volume methods. Yes, we are discussing finite volume methods. This can be used with uh, finite volume method, so it is not wrong, or it's not false with respect to artificial compressibility method. Next one is it eliminates the need for solving a separate pressure equation. So this is our solution, because here we are introducing a new term, artificial compressibility term, but not any new equations. So this is true regarding this is this is the false, the wrong statement regarding artificial compressive method, because we are introducing rho star is equal to p by beta square. So this thing factors that we have to solve this particular equation. So it actually brings a pseudo time loop from which we will be finding this p pressure. And also let's check the final option is true or false. It is a popular approach for simulating turbulent flows with incompressible conditions. Yes, we know this is brought for this particular method is brought into the picture only because the flow is incompressible. So our option is option C. So the thing is we may tend to not notice, because this we are uh, iterating a separate solution, separate uh, we are iterating a separate term or equation within a pseudo time loop. That is, this equation is, we will be iterating this part of the continuity equation. The our continuity equation becomes this. Actually, for a incompressible flow, del dot u is equal to 0, but when we introduce artificial compressibility, the equation becomes dou by dou t of rho star plus del dot u is equal to 0. And this term, this first term should be time marched to a steady state in a pseudo times loop. So we have to solve uh, for a pressure based sorry we have to solve a pressure related equation separately. How it is related to pressure? Rho star is equal to P by beta square. So here is pressure. Next question. A limitation of the artificial compressibility method for some of the application is. So you have to choose from the option listed below some limitations of the artificial compressibility method in uh, which is particular to some application, not a general limitation, but uh, for some particular conditions, which of the following factors of artificial compressibility method can become a hurdle? Options are difficulty in handling complex geometries. Option B, potential issues with interface capturing a multi-phase flows. Option C, inability to model heat transfer phenomena. Option D, incompatibility with existing CFD softwares. Options are: Option A, difficulty in handling complex geometries. Option B, potential issues with interface capturing in multi-phase flows. Option C, inability to model heat transfer phenomena. Option D, incompatibility with existing CFD software packages. Try to answer the question. So if you go through the options, so the keyword in this question is for some applications, not a general limitation. The question is about some application. So from this list of options, we can eliminate the last one, incompatibility with existing CFD packages. So this won't be some particular to any specific application, but it's saying that existing CFD software packages, all of them. So it's a generalized option. This we can eliminate. So the other three, uh, from the other three, again this complex geometry. Okay, complex geometry is also some particular application, but it is also in somewhat general, and also it has a general limitation with complex geometries. Again, we can eliminate this one. Also, these two things, these are about two particular applications. This is heat transfer phenomena. This is multiphase capturing. So the answer is in between these two. Also, the answer is uh, it has potential issues in capturing the multiphase flows. So when we have multi-phase flows, there will be some that is so in multi-phase flows there will be, I'm just drawing this as schematic. There will be more than one fluids, maybe yeah, water vapor, uh, I mean water and water vapor or any such combinations. There will be more than two fluids, and the interaction phenomena, the where these two fluids come into contact, that domain, to resolve in that domain, we will be needing some particular equations or particular methods. But our artificial compressibility method fails there because this is some portion where the pressure as well as the density of fluids, because there are two different fluids, the density will be different for these two fluids, and also the pressure acting upon the one fluid due to the presence of other fluid will be different. So in such cases, this capturing the interface of multi-phase flows will be a difficult thing for artificial compressibility method. So our option is option B. Moving on to next question. Which terminology best describes the role of artificial compressibility method in CFT solvers? So here is what is which of the following from the following terms, which is the best suited terminology for artificial compressibility method. Option A, turbulence modeling approach. Option B, preconditioning technique. Option C, direct numerical simulation method. Option D, boundary condition treatment. So from the list of options, you have to select the terminology that best describes the artificial compressibility method. Again, options are turbulence modeling approach, preconditioning method, direct numerical simulation method, boundary condition treatment. Again, it's a simple question. Try to answer the question. So from the list of options, we can what eliminate some of the options, because one is DNS, direct simulation method. This is some broad term which is not uh, particular to artificial compressibility method. And again, boundary condition treatment. This is not. We have already discussed what is artificial compressibility method, and it is not done on boundaries. It is for inner loops. I mean inner regions. So it is also not a boundary condition treatment. Again, turbulence modeling approach. It is ambiguous, so it can be used for turbulence modeling or not. But here, uh, the question whether it can be used for turbulent flows or not is another thing. But the purpose, general purpose of the artificial compressibility is not to model turbulent turbulent flows. So again, this is false, because we have discussed that whether it can be used for turbulent flows or not, we haven't discussed. But it's another question whether it can be used for turbulence or not. But the general purpose of the artificial compressibility flow is for, to model for incompressible. So how it is being introduced? And our only one option left is preconditioning method. So that is we will be uh, preconditioning. We will be applying some condition prior to the solving of our velocity terms, or we are but applying one particular criteria of raw star, uh, assuming an imaginary raw star such that it will help us in solving pressure of the system. So it's a preconditioning method, and also this raw star should be iterated till steady state. Also, it should happen the iteration of every particular instant, the iteration of raw star or this dou by dou t of raw star should happen prior to the main simulation. So it's a preconditioning technique. The answer is option B. Moving on to next question. While using artificial compressibility method, a good practice is to. So which of the following is a good practice while using artificial compressibility method? Options are: option A, set the artificial density to a very high value. Option B, continuously monitor pseudo time convergence process. Option C, utilize explicit time marching schemes exclusively. Option D, ignore the influence of artificial density in the final solution. So, which of the following is a good practice while using artificial compressibility method? Options are: set the artificial density to a very high value. Option B, continuously monitor the pseudo time convergence. Option C, explicitly time march schemes exclusively. Option D, ignore the influence of artificial density on the final solution. Try to answer the question. So we can eliminate some of the options here. So option D says to ignore the influence of artificial density in final solution. So from the option itself, you can uh, find that it's a wrong statement, because uh, to ignore an error. So influence of artificial density. Artificial density is something that you have introduced. So if you are ignoring that particular thing, that's something we have introduced, which is not a part of the system. We introduce it separately, and we can't just ignore it as such. And if we are ignoring that some source of error we intentionally added to the system, and we are ignoring it, then it won't be a good practice. So the final answer, sorry, the final option is not uh, true. We can eliminate that one. Then option C, utilize explicit time marching schemes exclusively. So explicit time marching schemes means when we are discretizing this term dou by dou t of rho star, so we will be having some uh, okay, I'm writing. When we are selecting some time schemes, we have to discretize this in a time domain, and that particular discretization in time domain should be explicit or implicit. So one I have discussed in earlier sections, explicit uh, explicit time marching. Explicit time marching is something that uh, apart from the unknown in the current time step, every other term in the discretized equation will be known. So we'll be finding the unknown, that is draw star at our particular time step will be calculated from all calculated entirely from known values. So such condition is called explicit time marching. But uh, here, because it's a pseudo time we are introducing, explicit time marching methods may not be feasible. That's again a wrong statement. Also, if we set artificial density to very high value, then it won't be having any effect on our system. So again, we are not uh, setting something to very high value, because unless it's a quality parameter for measure something, setting it to very high value won't be a good practice. Even if whatever the quantity we are setting it to very high value, then it won't be a good practice. The best practice is to set for an optimum values, because when we are setting something, not just artificial viscosity, if we are setting any mesh parameter or any other uh, parameter which we have the freedom to choose, and we are setting it to a high value, then it will have one or the other consequences. For Because we have to do some compromise when we opt for some high values. If we are opting for good, fine, very refined meshes, then computational time and computational resource will be greater. And also, if we are going for time step lesser, smaller, finer time steps, then computational length will increase. So, such that, uh, so similar to that, whenever we choose a very high value for any of the parameters in our CFD, it will be having one or the other consequences that will in turn affect our solving process or the solution itself. So all time, so this you can keep in mind that every time our idea is to find some optimum or workable. CFD is all about approximation of the real condition. So we will be more interested in finding some workable values. So our answer becomes option B, pseudo time convergence process. We have to monitor the pseudo time convergence process, because we have introduced a pseudo time iteration loop, and if we are not monitoring the convergence of that particular time, that is uh, this time dou by dou t of, I am writing this for every step, dou by dou t of rho star. This is iterated on a pseudo time iteration loop, and this should be this particular time iteration should be monitored, because only if this one converges, that is this one converges to steady state, then only we can uh, input the parameters, input this values of, or we can rely on the values of pressure that is being increased by this step. So the convergence of this pseudo time iteration loop has some weight on our computation. Next question: what are some limitations of the artificial compressibility method? So from the options listed below, which of the following are the limitations, or which one is the artificial which one is the limitation for artificial compressibility method? Option A, it can be computationally expensive for complex geometries. Option B, it may not be accurate as dedicated incompressible solver flow for all regimes. Option C, it requires significant user expertise for proper implementation. Option D, all of the above. Again, the options are: it can be computationally expensive. Sorry, 1 second. So the options are: it can be computationally expensive for complex geometries. It may not be accurate as dedicated incompressible flow for all regimes. Option C, it requires significant user expertise for proper implementation. Option D, all of the above. Try to answer the question. So, if we have already discussed that it can be computationally expensive for complex geometry. So this one is true for artificial compressibility method, and also it may not be accurate as dedicated incompressible solver for all regimes. So this one is also true. Second one, and so the final answer option D becomes true. And also uh, we have learned that we have a artificial time loop, that is a pseudo time loop, so which mandates some level of expertise. The implementation of pseudo time loop mandates the users to have some command over the program. So all of the options are true with respect to artificial compressibility method. Moving on to next question. The pressure equation in pressure equation in incompressible CFD aims to enforce which of the principle? From the options below, which one is the pressure equation? Which of the following concept is that pressure equation intends to enforce? Option A, conservation of energy. Option B, conservation of mass, option C, conservation of momentum, and option D, all of the above. So try to answer. Which one of the following principle is being enforced through pressure equation in incompressible CFDs? So it's a simple question because we have already seen we are implementing this artificial compressibility term rho star in our continuity equation. So our continuity equation is nothing but conservation of what? Conservation of mass. So it's a very simple question. So you have to only check where we are implementing this roster. We are implementing this roster in our conservation of mass equation or our continuity equation. So our option becomes option answer becomes option B, conservation of mass. Next question. In a collocated grid arrangement, it's another concept in our pressure equation solving. In a collocated grid arrangement, which variable is typically stored at the same location? Options are option A, pressure and velocity. Option B, pressure and density. Option C, velocity at all directions. Option D, none of the above. So the question is for collocated grid arrangement, and in collocated grid arrangement, which of the variables are stored at the same location? Try to answer the question. So collocated grid arrangement. So if you can split the uh, word collocated, it is co-located or co-allocated. You both ways you can read it. So something is co-allocated. That that particular thing is there, or if you are reading this co-allocated, something is allocated in this in one place simultaneously. Suppose if we can draw a grid. So in this grid, when we are solving for velocities as well as pressures, then we will be have to solve for two set of equations. So uh, how we can solve these two sets of equation? So in collocated grid, these uh, two things, that's pressure and velocities, we have to find because we have seen that velocity is being found out from one set of solution, whereas pressure is also coupled to velocity using some other equations, either with equations of state or being some with some equations like artificial compressibility. So where these things are being stored, which of the following things are stored simultaneously at one location? In uh, collocated grid arrangement, the pressure is located at cell centers. This is the cell centers. Then these are the points where we store pressures. So P. These things are being found at cell centers, and also velocities will be at the faces. So we will be storing pressure as well as velocity at the same cell. We won't be needing separate grids or separate meshes, not meshes, sorry, separate grids to uh, store the values. So our answer is pressure and velocity. Next one, on another method of pressure solution. In a staggered grid arrangement, a primarily used uh, a staggered grid arrangement is primarily used to address which of the following CFD simulation. So what is the main purpose, or what is where we need some staggered grid arrangement to what to establish in a what which kind of the situations mandates or requires a staggered grid arrangement. Options are uh, tabular modeling, option B heat transfer calculations, option C pressure velocity coupling, option D grid generation complexity. So which of the following uh, conditions mandates or requires a staggered grid arrangement? Options are turbulence modeling, heat transfer calculation, pressure velocity coupling, grid generation complexity. Try to answer the solution. Sorry, try to solve the question. Okay, in staggered grid arrangement, Actually, there will be two set of grid if you can see. So here in staggered grid arrangement, uh, there will be two grids or two different locations. So where one particular grid or set will be used for solving one particular location will be used for uh, storing pressure, and other grid is for solving velocity. So the this particular question's answer becomes pressure velocity coupling. So and how it is done is that one particular mesh is used for pressure, whereas uh, uh, velocities are being calculated with other mesh or other location. So we'll be needing two different locations for pressure and velocity, and this will be uh, by saying uh, two different meshes. What we uh, what what we mean from being two different machines is that we will be storing the values of pressure and velocity for different spatial values. We will be storing the values of pressure and velocity at different locations. That is what we mean by staggered grid arrangement, and it is used for pressure velocity coupling. So next question is like in the context of pressure correction methods like simple, what does P represent? The options are initial guess for pressure, option B pressure at the next time step, option C corrected pressure value, option D pressure difference between neighboring cells. Try to answer the question. So again, this simple, the simple method is something used for finding again solving pressure equations. So the thing is, the question is, what is the P in the simple represents? So what is this symbol? Symbol, the full form of symbol is semi implicit method for pressure linked equations. So if you are taking the first names SIMPLE, we get simple. So the question is, what does this P represents? P represents pressure. So our options don't stop there. Our options are which pressure. Now we know it is pressure. The P represents pressure, but which pressure is represented? Which represent is being giving the significance, which pressure is being particularly denoted by this pressure term in symbol. So options are initial guess of pressure, option B pressure at the next time step, option C corrected pressure value, option D pressure difference between neighboring cells. So in symbol, what we will do is we will bring in some equations to uh, help us solve the pressure equations. So these equations are being introduced in such a way that, so from the this name semi-implicit itself, we can understand that it is having some implicit. Implicit means some unknowns. So it means implicit. We already discussed that when system is fully explicit, we will be calculating our unknown value, one unknown parameter from all non-parameters. In implicit, we will be uh, uh, finding or solving our unknown value from set of unknowns through iterative methods. So here it is said that semi-implicit. So we will be calculating our unknown from knowns and unknowns. So such kind of method is called semi-implicit method. So in semi-implicit method, what pressure is being used? In simple method, we will be introduced to some equation like P is equal to P star plus P dash. So where this P star is called the corrected pressure. Sorry, this P star is uh, P star is the known value of pressure from the old iteration, or known value, and this P dash is the guess or correction or pressure correction, corrected pressure. So it is this P that is being stressed in our symbol. So our actual pressure P is a corrected pressure. So corrected pressure is equal to P star, that is the old or known value of pressure plus a pressure correction. And this corrected pressure is being what we are be using in pressure linked equations or symbol. Our option is option C. By the pressure in symbol, by the pressure time in simple, we use the correct pressure given by P is equal to P star plus P dash. Moving on to next question. Which interpolation scheme is commonly used with staggered grids to determine phase velocities for pressure equation? Our question is to which of the interpolation schemes are used with staggered grids to determine phase velocity for pressure equation? Options are option A central differencing, option B upwind differencing, option C reach-out interpolations, option D least square method. I got the question. So from the above, we can see that least square methods is not what we are following in most of safety methods. So from this three things, you can uh, uh, these four options. If you see, there is the asking is interpolation scheme. So in central differencing and upwind differencing is a discretization scheme rather than interpolation scheme. Interpolations is something that interpolation is a process when we have some values. Suppose if you know this ABCD values, then how can you find some value in between, or how to find these values in between? So all these things is a interpolation method. Uh, this is called interpolation. Suppose we know these values A, B, C, D, and we are defining some. It follows these values follow some trend, and with that trend we can find this. We can find or interpolate when we have a data set and we have to find some value in between. So that process is called reach. I mean interpolation, and one basic method for interpolation is least square method, but it is not as such used in our CFD processes because it requires a lot another set of statistical calculations or another set of calculations. So we are not using least square method as such. So in our pressure velocity scheme, a most common interpolation scheme used is Raychow scheme. Raychow interpolation is used not only with staggered grid, it is also used with collocated grids. So Raychow interpolation is something uh, that help you uh, find the values of pressure at the same point where velocity is. So in staggered grid, we told that in staggered grid, P and velocity different locations. So with Riccio interpolation, we can interpolate the pressure at the position of velocity. So it is like I have already shown the staggered mesh thing, the how it is stored differently. So that particular thing can be uh, even though the pressure and velocities are calculated at different location, the Riccio schemes can be used to interpolate the pressure at the point where velocity is being calculated. Moving on to next question. A key advantages of using staggered grid for incompressible CFD simulation is. So the question is asking the advantage or the key advantages of staggered grids. Options are A. Reduced computational cost. Option B. Improved accuracy for turbulent flows. Option C. Easier implementation of boundary condition. Option D. Enhanced convergence for pressure velocity coupling. Options are reduction in computational cost. Option B. Improved accuracy for turbulent flows. Option C. Easier implementation of boundary conditions. Option D. Enhanced convergence for pressure velocity coupling. So to answer the question. Okay, if you can go through the options itself, you can easily eliminate the options. The first option is saying a reduced computational cost. So when we are having a staggered grid, I told you two different grids will be there or two different set of locations. One set of locations for velocity calculation and another set of locations for pressure calculation. So what it essentially means? It essentially means there is an increased computational cost. So the reduction in computational cost is not visible because in staggered grid pressure and velocity in different grids or different location. So that makes this option wrong because when we have to fix locations for pressure calculation and we have to fix locations for velocity calculation and we have to simultaneously solve both set of equations. So which will in turn increase the computational cost. Next question is improved accuracy for turbulent flows. So turbulent flows is having another set of equations for we know if you have read about turbulent flow modeling and all, we will be having some modeling for turbulent flows. We have to model the velocity components to such that uh, what is the extent of turbulence we want to find. So the turbulent force itself is difficult. Turbulent modeling itself has some another set of algorithm. So if you are using staggered grid in turbulent flows, it will again complicate things. So let alone let alone the accuracy, the implementation of staggered grid in turbulent flows itself is difficult. So again, option B is strong. Then option C, easier implementation of boundary condition. That that's intuitive that it is also wrong because when we are calculating uh, pressure and velocities at different locations, there will be some difficulties uh, in boundary condition. The boundary condition is that we have to at the boundaries we will be setting some values for your pressure or velocity. So that itself will be if we are giving velocity boundary conditions, then at the boundaries to solve pressure equation we will have to find, suppose we have a problem and we have some inlet velocity and outer pressure, then by using staggered grid, the, we will be applying velocity as some values of velocity as the inlet condition, and with help of that we will have to solve for pressure. We will have to find the values of pressure at the boundaries. Then only we can solve for pressure in the pressure grid. So option C is again wrong. Our answer become option D, enhanced convergence of pressure velocity coupling. So the purpose and advantage of staggered grid is pressure velocity coupling. So our answer is enhanced convergence of pressure velocity coupling, which will be leading to a more stable and efficient solution for pressure equations. Next question. Which of these statement is false regarding pressure equation in incompressible CFD? Option A, it can be derived from the continuity equation. Option B, it involves the equation of state for the fluid. Option C, density is treated as constant variable. Option D, it plays a crucial role in capturing shock waves. So again, a simple question. Try to answer the question. Yes, we can. The answer is most evident that density is treated as a constant variable for because we will be using uh, uh, equations of state. We'll be using equations of state to couple or to solve for pressure equations, and equations of state as well as the continuity and momentum equations will be having density term, which will be a variable, not a constant. So compressible CFD accounts for density variation. So density being treated as a constant variable is a false statement regarding compressible CFD. Moving on to next question. When using finite volume method for pressure equation, what represents a control volume in centered grid? So the question is, when uh, what is a what represents a control volume in a finite volume method for pressure equations? Option A single grid point. Option B, the entire computational domain. Option C, a cell surrounding a pressure point. Option D, the space between neighboring velocity point. So it's the question is about representation of a control volume in staggered grid for pressure equations. So how you will be representing the control volume for pressure equation in a staggered grid. Try to answer the question. So I have drawn earlier. I have drawn two different measures for staggered grid arrangement. If we can draw it in single structure, because this mesh in I don't have to draw a lot different lines, but I'll have to represent the position of pressure as well as velocities in single mesh. Then how will I do it? Then the center point will be represented with the pressure, and phases will be velocities. With the help of that, try to solve that question. So uh, these are two locations where pressure and velocity is being stored. So the question is control volume. So question is about the control volume of the pressure equation, so pressure for the pressure equation. So when we are taking this center point as pressure storage, then the control volume. So the volume surrounding this pressure point will become the control volume. So the option is option C, a cell surrounding the pressure point. Next question. A disadvantage of using staggered grid compared to collocated grid can be. So the question is about comparison between staggered grid and a collocated grid, which is a disadvantage of staggered grid over collocated grid. Options are option A, increased memory requirements. Option B, simpler implementation of source terms. Option C, more complex interpolation procedures. Option D, improved stability for high Reynolds number flows. So we already discussed that what is the main difference between staggered grid and collocated grid. In staggered grid, the pressure and velocities will be stored at different locations. At collocated grid, it will be simultaneously stored at same location. So what is the disadvantage of staggered grid over collocated grid? try to answer the question. It's another simple question. Okay, with that knowledge, if you are trying to answer the question, so the first question, this one itself, you will feel right, because when the uh, pressure and velocity are being stored at two different locations, it will be having increased memory requirements. It is true, but if you choose the other options, uh, that next option is like simpler implementation of source times. So that is wrong. And option C, more complex interpolation procedures. This is also true. Or actually, this is uh, this should be highlighted more with respect to the first one. So more suitable option is option C rather than option A. Increased memory requirements are there, but main disadvantage, this increased memory requirement can be uh, taken as a drawback, not as a disadvantage, but more complex interpolation procedures that we have to apply some interpolation procedures to solve for uh, pressure or velocities, because we have to find the pressure at the location of velocity, so it will be needing some interpolation procedures. So that is a disadvantages when using staggered grids. So a best answer is option C rather than option A. So this is also true. This is kind of a trick. When you have seeing the first uh, option itself, you will go for it. But this is true, but that you can't directly say as a disadvantage, but it is rather a drawback of the or limitation of the staggered grid approach, where this one is a more serious disadvantages of this particular procedure. So our option is option C. Next question, which of these term is not typically included in a pressure equation for incompressible CFD? Our options are a pressure gradient time, option B a convective velocity time, option C a viscous stress time, option D source time. Here if you see that the terms for while solving for pressure equation, the terms which we don't use is the convective velocity type. Option B is the answer. Next question. The pressure equation in incompressible CFD is derived from which of the governing equation? Options are option A, energy equation, option B, continuity equation, option C, momentum equation, option D, ideal gas law. So from these laws or equations, which is the governing equation used for pressure equation in the incompressible CFD? That's again a repeat question. The same concept asked in different way. Try to answer the question. Yes, the answer is continuity equation. We have discussed in before also in another way. That's the pressure equation is in artificial compressibility and all other things. And the mostly the standard or fundamental governing equation for used for pressure equation to uh, develop pressure equation is the continuity equation. Next question. In a staggered grid, the pressure is stored at. So this is again same concept asked in different way. What is the location of the storage of pressure in a staggered grid? Options are cell faces, cell centers, vertices. It can be stored anywhere on the grid. Try to answer the question. Again, a simple question. Yes, the answer is cell centers. I already said that for a staggered grid arrangement, the pressure will be stored at the center and velocity at the faces. So our answer is cell centers. Which of the following is an advantages of using staggered grid? Up to this time, we are discussing about the disadvantages or drawbacks. So the next question is, which of the following is an advantages of using a staggered grid? Options are simpler implementation of boundary conditions. Option B, easier to calculate gradients. Option C, requires less memory storage. Option D, more intuitive for visualization. Right to answer the question. Options are simpler implementation of boundary conditions. Option B, easier to calculate gradients. Option C, requires less memory storage. Option D, more intuitive for visualization. So you can easily eliminate some of the options. The request less memory storage is not an advantage. It's rather wrong statement. We need more memory storage. Uh, Next one, similar to apply boundary condition, that also we have discussed in some other question, that it is also a disadvantages of stacked grid. Then more intuitive in visualization. This is again wrong because this staggered grid can cause trouble, something called checkerboarding. This can induce something called checkerboarding. So this is not intuitive for visualization, but it is uh, better when we need to calculate the gradients. So the advantage of a staggered grid is that it is easier to calculate the gradients in the staggered grid. Next question. A pressure velocity coupling issue arises in CFD due to which of the following? What is the requirement for pressure velocity coupling in CFD? Options are A. Nonlinearity in momentum equation. Option B. Turbulence modeling. Option C. Incompressibility constraint. Option D. Higher Reynolds number flows. So we have already discussed why we need pressure velocity coupling. The pressure velocity coupling is a main factor or requirement when there is an incompressibility constraint. Also, pressure velocity coupling creates issue uh, uh, is required when there is non-linearity in momentum equation. But from uh, from the viewpoint of our this week's lectures, this is the option C. Answer is our option C, incompressibility constraint. Next one, next question. The symbol algorithm is commonly used with staggered grid 4. So when do we use symbol algorithm with the staggered grids? Option A, viscous correction, viscous stem discretization. Option B, boundary condition implementation. Option C, turbulence modeling. Option D, pressure correction. This is also easy question. Try to answer that. We have already discussed that the P in symbol pressure that we are inferred in symbol algorithm is the corrected pressure. So with that knowledge, it is easy to answer the question. So symbol algorithm is used for pressure correction. Next question is about uh, vorticity stream function and vorticity stream function of modeling for pressure correction. Sorry, for pressure equation solution or to solve pressures. So the stream function vorticity formulation solves which of the two fundamental variables in two-dimensional incompressible flows. So the question is, what is the stream function vorticity formulation solves? Which of the equations is the stream function vorticity equation solves? Stream function method, what is stream function vorticity method is another method used uh, to solve for pressure in uh, uh, in incompressible flows. So options are velocity u and v components. Option A. Option B, pressure P and vorticity. Option C, stream function and velocity U. Option D, stream function and vorticity. Again, in this question, it is a much simpler question. You can see that the question itself is stream function vorticity formulation. So in stream function vorticity formulation, which of the equations are being solved? It is very intuitive from the question itself. It is stream function and vorticity equations uh, that are being solved for or the variables that are being solved for in this kind of formulation. Next one, it is from basic fluid mechanics. What is the mathematical relationship that exists between stream function and velocity components in two-dimensional flows? So from the given list, which of the mathematical relationship is true for relationship between stream function and velocity components? Option A, u is equal to dou phi by dou x, sorry, dou psi by dou x, and v is equal to minus dou psi by dou y. Option B, u is equal to minus dou psi by dou x, and v is equal to dou psi by dou y. Option C, u is equal to dou omega by dou x, and v is equal to dou omega by dou y. Option D, u is equal to omega into x, v is equal to omega into y. So, say question from basic fluid mechanics on basic understanding of the stream function. The options are option is B. Option B is the true answer. The stream function psi is chosen such that u is equal to minus dou psi by dou x and v is equal to dou psi by dou y, so that the Laplacian, the del square psi, will be 0, such that stream function is stream function psi is chosen such that del square psi, that is the Laplacian of psi, becomes 0. So this equation is what that meets that what we have chosen for the formulation of stream function. But if you see, this will also uh, gives the same answer, but uh, and that will also that will also uh, agree with Laplacian of del square psi is equal to 0. But by convention, we have chosen u is equal to minus dou psi by dou x and v is equal to dou psi by dou y as the relationship between velocity components and stream function. Going to next question. The vorticity Omega in a stream function vorticity method represents what? Option A, divergence of the velocity field. Option B, rate of rotation of fluid element. Option C, pressure gradient in the flow. Option D, viscous dissipation rate. So what is the term vorticity in stream function vorticity method represents? This is also a question that you can relate to fluid mechanics, fundamental fluid mechanics. So if you remember what is vorticity from fluid mechanics, then it is simple. So vorticity is given by del cross u is equal to 0. Or del cross u, this is what the term given by vorticity. So this is a cross product of del and u. So any cross product or the another name for cross product is curl. So curling is about rotation of a vector. So we can relate to this one. That is, vorticity is about rate of rotation of the fluid element. Next question. A key advantage of the stream function vorticity method is. The question is about advantage of stream function vorticity method. Options are direct calculation of pressure without requiring Poisson's equation. Option B, efficient solution for flows with complex geometries. Option C, straightforward implementation of boundary condition for velocity. Option D, improved accuracy for high Reynolds number flows. You can try to answer that question. So if you go through the options, some it is easy. Suppose if you understand what is stream function vorticity method, here we will be replacing u and v velocities with the stream functions. So we have already seen that u is equal to minus dou psi by dou x and v is equal to dou psi by dou v. So we will be replacing u and v with this functions. So we will be converting into a system equation psi. So with this method and also we will be using del cross u, that vorticity function, to solve the system of equations. So if you see some of the things can be easily eliminated. Some of the options can be easily eliminated because this option C is very much wrong. The straightforward implementation of boundary conditions for velocity. This is wrong because when you are converting u to psi, then you will also have to convert the boundary conditions BCs of u to BCs of psi. So that process itself is a difficult process. So this option is wrong. And also efficient solution for flows with complex geometries. That will again become wrong. Becomes because when the complex geometry with the geometry getting complex, the modeling of psi in terms of u and v will be again difficult. So improved accuracy in high number flows. High Reynolds number flows means turbulent flows or something. So there again, this stream function vorticity methods won't be good. Then the only option left is that direct calculation of pressure without recurring Poisson's equation. So uh, uh, it is not a key. You can't say it's a key advantage, but thing is we are not solving Poisson equation for pressure here. So that's something true with respect to stream function vorticity method. But uh, we will be solving the Poisson equation for vorticity and stream function. That is, we will be solving this Poisson equation dou square psi by dou x square plus dou square psi by dou y square is equal to minus omega z. This Poisson equation will be solved in order to solve the system of equation. But we will be solving something for pressure. This is solved for psi. Next question. A limitation of stream function vorticity method for boundary condition involves. Options are specifying both stream function and vorticity at all boundaries. Option B, difficulty in implementing no-slip boundary condition on solid walls. Option C, inability to handle flows with free surfaces. Option D, all of the above. So we have already discussed that uh, there is difficulty in defining boundary conditions for vorticity, stream function vorticity method. So this question is specific about that particular statement. Which of the following is a limitation with respect to setting boundary condition for stream function vorticity method? The answer is all of the above, because it will have faced difficulties in all these, uh, because there are two functions, velocity and vorticity. It's not just u or v. We have to find stream function and vorticity at all the boundaries. So the converting or uh, finding and this uh, converting our boundary conditions in u and v to that of psi and omega will be difficult. And also in lateral walls, in other than the direction of flow, lateral walls, we what we use in CFD is no slip boundary conditions. So no slip boundary condition is again difficult in solid walls, because stream function, if you remember from basic fluid mechanics, stream function is something that related to streamlines. So streamlines, and again vorticity is the omega is the rotation. So with these two things, with these two uh, things, uh, converting it in no slip condition is difficult. Again, at free surfaces, the same issue occurs, where in free surfaces, what we use is no shear. No shear is the uh, boundary condition that we apply for free surfaces, again setting that boundary condition becomes difficult. So of the all the three things becomes difficult in uh, stream function vorticity method. So our option is option D, all of the above. So that's all for today. Thank you.